Hello, everyone. I'm Mary Wheeler from the University of Texas and want to welcome you to a discussion of our framework on Bayesian optimization for field-scale carbon sequestration. And I want to comment on our collaborators, Cherry Liu, who will really describe more of the physics and the calculations that be carried out, Kirk Jordan, who has really been the leader in this effort of combining the physics of carbon sequestration from the work with IBM on their Bayesian optimization. And of course, want to thank Edward and Matthew for their assistance in all this. We couldn't have done all this work without their help. I would like to comment on the motivation for this UT-IBM cooperation. The proposed framework really represents a first attempt at incorporating high-fidelity physical models and machine learning techniques for data assimilation and optimization for geological carbon sequestration for field-scale applications. This methodology, which is quite complicated for this problem, can be applied to other physical models such as subsidence, hydraulic fracturing, and many biomedical applications. Why is this important today? Well, we go back to the goal of the 2015 Paris Climate Agreement. The United Nations claims that carbon removal technology is necessary for limiting increases in planetary warming to more than 1.5 degrees centigrade. This one was also commented on by Sally Benson. She is co-director of Stanford's Precourt Institute for Energy. And this was done at the 2020 SPE Improved Oil Recovery Conference, in which she stated that climate change mitigation and continued oil production are not necessarily mutually exclusive. And here's where CO2 EOR is particularly important. For example, if we double the amount of CO2 that's injected for every barrel of oil that's taken out, we will reach carbon neutral transportation fuels. Now, what we're seeing happen are recent commitments and initiatives. In particular, ExxonMobil created a division to commercialize technology for reducing carbon emissions. This was just announced this February. They plan to invest $3 billion on lower emission solutions through 2025, aiming to reduce its oil field greenhouse gas emissions by 15 to 20% from 2016 levels. And in particular, they are starting projects in the US Gulf Coast, Wyoming, Netherlands, Belgium, Scotland, Singapore, and Qatar. These new projects will complement ExxonMobil's current carbon capture capacity in the US, Australia, and Qatar, which totals about 9 million tons per year. Another effort is an Oxy's US Rockies business unit. Brian Owens, who's a senior VP at Oxy, indicated that in this Midwest CO2 superhighway initiative, that they would have a cross-industry endeavor that will take CO2 from a mix of industrial plants in the interior of US and move it hundreds of miles south to aging oil fields in the Permian Basin of Texas, where EOR infrastructure already exists. This project is a major undertaking to acquire new CO2 pipelines spanning 7 states that has the potential to reduce the US total emissions by 4% through carbon capture and sequestration of 40 million metric tons of CO2 each year. Now, we have had some industrial scale projects, such as the Illinois Carbon Capture and Storage Project, where here over 1 million tons of CO2 were injected. This was completed in 2014, and this study really created a very nice knowledge base, geological characterization, risk assessment coupled with reservoir modeling, which of course is extremely important, as you can see from these slides, and in which you will hear more about in our presentation. Now, to really briefly give you some of the challenges. Like I said, this is really one of the first steps in trying to really couple large-scale machine learning data assimilation techniques with physical models. That here we have a large basin-scale storage site. We need to monitor over a long period of time. We have heterogeneous rock properties. So, for example, our numerical grids contain scale-variant, non-linearly connected in space-time dependent information that will impact flow behavior. CO2, water, rock interactions, and a significant mineralization or geochemistry effort that needs to be involved. Unstable CO2 migration due to density and viscosity. This is numerically challenging. And then, of course, rock mechanics and caprock integrity. Now, I'm going to turn this over to Cherry Liu, who will now talk about the gas mobility control and carbon sequestration, Bayesian optimization introduction, and how this Bayesian optimization plays in field scale carbon sequestration, and then summarize what our efforts have been in this area.
Okay.
Cherry?
Yeah, thank you, Dr. Wheeler, for the nice introduction. So I will give the technical part of this talk. So first, I would like to talk about briefly the geological carbon sequestration. So after carbon dioxide has been captured from a source, like a power plant, it is transferred to and injected into an underground geological formation, such as an alien aquifer or a depleted oil and gas reservoir. Now, the challenge of continuous CO2 injection is that it suffers from low gas sweep efficiency because of low gas density and low gas viscosity. And the experience from EOR is that by alternately injecting water and gas, we can improve the sweep efficiency. And moreover, by surfactant alternating gas that can generate foam in situ, it further increase the sweep efficiency by reduce the liquid gas mobility ratio and therefore push the gas into the lower permeability part and the deeper part of the reservoir. So the objective of this collaborative research is to couple IBM's Bayesian Optimization Accelerator with the reservoir simulator IPARS to optimize how do we best inject this CO2 and the surfactant. Let me first give an overview of our simulation workhorse, IPARS. So it contains several physical modules. For example, for flow module, there are compositional flow that is used in this research, and also black oil and single and two-phase. And for geomechanics, there are poral elasticity models and poral plasticity models, and they are all coupled with the flow model. For this study, there are these advanced petrophysical models that allows an accurate characterization of the surfactant alternating gas process. And IPARS has been coupled to several different optimizers, for example, the Bayesian optimization, and also data assimilation algorithms like ENKF. So a little bit more about the compositional flow model. It assumes that the fluid has 3 phases and an NC number of components, and it uses flash calculation for hydrocarbon phase behavior. And it assumes that hydrocarbons are fully compressible and water is slightly compressible. For the governing equations, there are mass conservation for each component and Darcy's law for each phase. So why use Bayesian optimization? Many workflows require you to find a powerful set of parameters to solve a problem. The challenge is to find these parameters robustly as in little time as possible. And Bayesian optimization is a powerful method for doing this. There are two major tricks in Bayesian optimization. The first is to utilize a Bayesian surrogate model to replace the true objective function. The second is to take into account both the model predictions and the uncertainties to decide on what decision to make. However, why isn't all optimization Bayesian? Because the standard Bayesian is fragile to prior specifications and it only supports for serial executions and it has limited scalability in high-dimensional problems and because of unintuitive softwares. And I will address these issues later. Here is a high-level algorithm overview of Bayesian optimization. So we start by building a probabilistic surrogate model of the objective function, which is often a Gaussian process. And then we compute the posterior predictive distribution that integrates out all the possible true functions. And then we build an acquisition function, which is much cheaper to optimize than the true objective function. So the key in this process is to use uncertainty in the posterior to balance explorations and exploitations. Again, in a nutshell, the Bayesian optimization is consisted of two parts. The first is the Gaussian process model. As shown on the right-hand side of this slide, shows a very simple 1D Gaussian process. On the left picture shows the prior that has a mean of 0 and a variance of 2. These different curves with different colors represent different samples from the prior. And on the right-hand side shows the posterior distribution after several observations that are marked as the plus sign here. So we can see that the means and the posterior covariance, the gray area has been updated based on the observations. And upon that, we use an acquisition function that balances exploration and exploitations to decide the sequence of evaluation points. So the acquisition functions, there are three kinds of acquisition functions, like the improvement-based, the entropy-based, and the confidence bound-based. And here we'll focus more on the improvement-based acquisition functions. And IBM researchers has developed this contextual improvement-based acquisition function that gives an adaptive variant for minimization and also removes a meta hyperparameter. And this method is also shown to be more robust to poor priors. And here's a reference of the technical paper that you may find more technical details. Besides that, IBM researchers has also developed several parallel Bayesian optimization algorithms. For the time's sake, I'm not going into the details of this, but here's the reference of the technical paper. So this is how we couple IBM's Bayesian optimization accelerator to IPARS. The IBO is running on the IBM cloud, and the reservoir simulator IPARS is running on UT's in-house cluster. We use this interface function that it can generate IPARS input files and then substitute it in the query points generated by IBO, and then submits IPARS jobs that can be run concurrently in parallel. And after all the jobs are done, it post-processes the IPARS output data and calculate the objective function and pass it back to IBO. Now here is the data on the Cranfield site that is used in this case study. So we modeled 6 actual injection wells from the Cranfield site. For the reservoir model, we also put some pseudo boundary wells that can mimic an open flow boundary condition. Here are more reservoir more data on the reservoir model. So this model has around 500,000 grid blocks. We used history-matched full tensor permeabilities and the relative permeabilities. Here are some data for the compositional flow model. And this slide shows the simulation result of continuous CO2 injection in comparison to surfactant alternating gas. As we can see that SAG can significantly improve the sweep efficiency and CO2 storage volume. So here we would like to optimize the global CO2 storage volume given a specific amount of time. So here the parameters are the length of each of the CO2 and surfactant injection period, and the objective function is the cumulative CO2 storage volume in a specific year, and here is 20 years. So here is our experiment results. On the left-hand side, we can see the effect of optimized SAG compared to continuous CO2 injection, that it significantly improves the sweep efficiency and the CO2 storage volume. We also compared the performance of IBO to other commonly used optimization algorithms, such as genetic algorithms and covariance matrix adaptation evolution strategy. And we found that IBO can achieve a better optimum value with much less number of function evaluations. And this is important because we all know that one run of reservoir simulations is expensive. Here are the conclusions. So the proposed framework represents a first attempt at incorporating high-fidelity physical models and machine learning techniques for data assimilations and optimizations for geological carbon sequestration in field-scale applications. Specifically, the Gaussian process regression and the use of the acquisition function allows an efficient exploration of the surrogate solution space, and the underlying physical models strictly honor the complicated physics during geological carbon sequestration. And this methodology can be also applied to other physical models such as subsidence, hydraulic fracturing, and even biomedical applications. And this Bayesian framework naturally quantifies the uncertainty associated with the processes. And for this study, a benchmark with commonly used genetic algorithm and evolution strategy demonstrates a very high potential for further application of Bayesian optimization. With that, I will end this talk. Thank you very much.